Alright, I am going to pick up where we left off on IR spectroscopy now. So we saw there's three things to look at that we want to analyze: wave number, size, and shape of the peaks. I want to go back to wave number. And what's interesting about this is you can actually see a trend, a couple of little trends develop in terms of how you can sort of generally predict relative positions on the wave number chart. Okay? I said earlier that you can sort of think of these bonds as being very spring-like. Excuse me. We can actually draw a very, very good analogy to a traditional physics experiment. All right? If any of you guys have had physics or are currently in physics, you may have heard of something called Hooke's Law. And Hooke's Law, what it is, it's a formula that describes the motion of a spring. Right? If you were to take a spring and hang it up, or hang a spring off of a hook, like this, and you were to pull that spring back and let it go, what's it going to do? It's going to sort of bounce back and forth, right? It's going to oscillate. And it's going to do so at a certain frequency, right? Well, basically, in a large part, this is what our stretching vibrations are doing when looking at IR spectra, right? We're looking at a lot of stretching vibrations. There's actually a variation of Hooke's Law formula that's actually been modified specifically for use in IR spectroscopy. Let me show you what it is, all right? This refers to wave number. So wave number equals K times the square root of F over M. Okay? K is just a constant value. We're not really going to worry about that one. The two that are more interesting are this, F. That's a force constant. And that is related to strength. All right. M refers to mass. All right. So let me sort of show you what's kind of neat here in terms of Hooke's Law, and I'm going to use the spring analogy again. All right. Let's say you had a physics experiment where you had two hooks. All right, and you had two springs. I want to draw one of the springs right over here. And I want to draw the other spring over here. Okay, now you'll notice I drew them kind of differently. The spring on the left is supposed to represent a very, very tightly coiled spring. And the spring on the right is one very loosely coiled, sort of like a slinky. If you don't know what a slinky is, Google it. All right, and so on each one of these springs, I'm going to have attached a mass. And they're going to be identical to each other. Let's just say 100 grams for both of them. And what you do is you let go of the mass, and you watch the spring then bounce back and forth or oscillate at a certain frequency. Right? So if we do this to both of these springs, let me ask you, which spring do you think is going to bounce back or oscillate with a higher frequency? Is it going to be the tightly coiled spring or the very, very loose spring? I would hope you would say that this one, the tightly coiled spring, would oscillate faster. And that means it's got a higher frequency. All right. Well, how can we relate this to bonds, chemical bonds? All right. Well, let's compare three bonds here. Let's compare a carbon-carbon triple bond, a carbon-carbon double bond, and a carbon-carbon single bond. All right. And in previous classes in Gen Chem, you probably talked about strength of bonds. So ask yourself, out of all these three, which one's the strongest bond? Single, double, or triple? Right? It should be this one. That's the strongest bond. and the shortest bond, right? Very, very similar to a tightly coiled spring. So if you're thinking about the stretching vibrations of a CC triple bond versus, say, a CC single bond, right? It's going to be much faster. It's going to oscillate at a much higher frequency than the one that has just the single bond. And you can actually look in a correlations table and see that this works out. Carbon-carbon triple bond tends to absorb right around 2200 inverse centimeters or so. Carbon-carbon double bond about 1640. Carbon-carbon single bond is going to be, in various states, less than 1500. Okay? Also, you can see this work out mathematically in the Hooke's law equation. All right, look at our force constant. This is what we're relating to strength, right? So basically, as you increase the strength of your bond, you increase the value of F, all right? Mathematically, in this equation, what happens as you increase the value of F? The value of nu, wave number, goes up, right? Wave number is directly proportional to the square root of the force constant, or strength, right? So the stronger the bond, the higher the wave number that it will oscillate at. All right, let's take a look at another hypothetical Hooke's law experiment. Again, we're using springs as the example. So in this case, we're actually going to be using two identical springs, or at least as identical as I can draw them, but we're going to have two different size masses. Let's say that one's 100 grams. Let's say that one's 1,000 grams, or 1 kilogram. Okay? And you could do the same thing. You drop them, and you measure how fast it takes for the springs to bounce back. In this case, I would hope that you would be able to figure out that the one with a lighter mass is going to oscillate at a higher frequency. Right? Whereas the one with a heavier mass, it's going to be pulled further down. It's going to take longer for it to come back up, etc., etc. Right? All right, well, again, keep that in mind. We're going to compare a couple of different bonds here. CO single bond and CH single bond. All right? So looking at these, what's the only difference between these two bonds? That's going to be whatever is attached to the carbon, right? In both cases we have a carbon. In both cases we have a single bond. One of them we have an O, one of them we have an H. Guess what? Those atoms have different masses. The hydrogen, of course, is going to have a lighter mass than oxygen. And that's going to be analogous to the lighter weight that we used in the hypothetical spring experiment. So what do you think the oscillation or the frequency is going to be for a CH bond relative to CO? It's going to be higher, right? It's going to have a higher wave number. And again, you can see this in the formula as well. How does wave number relate to mass? Wave number is inversely proportional to the square root of the mass, right? So as the mass goes up, the wave number goes down. All right. So those are some things that you can. Those are a couple of things that you can keep in mind whenever you're taking a look at two different types of bonds and trying to figure out, their relative positions on an IR spectrum. All right. So next, I want to go over. I just kind of want to highlight some of the more prominent representative peaks for each one of the functional groups. I'm not going to lie, this part's a little dry, and there's not really a whole lot I can do to spice it up. I'll try to keep it as interesting as possible, but hang in there. This will help you as you're trying to interpret things in the future. All right? So, let me go back to this tutorial. All right, and I'm going to start at the very beginning with alkanes. All right, so alkanes, they're kind of boring, right? They have nothing in them but two different types of bonds. they have CC single bonds and CH single bonds. All right. Now, if you look at an IR spectrum, come on, there we go. Here, for each one of these, it has some common ones listed. Not all the ones they list are really that reliable, so I'm going to highlight the ones that you care about most. For alkanes, really, the only useful one is going to be the stretch from 3,000 to 2,850. That's really the only one that's reliable. That's typically a really strong, really sharp peak, and it usually appears as a cluster of peaks, right? So you see here, we have a nice little cluster of peaks in that range. They're always slightly below 3,000. So if you see a cluster of peaks here and really nothing else of note in the functional group region, that's a pretty decent indicator that you have an alkane, right? You do see some other stuff appear here, but it's all in the fingerprint region, right? So what you see for this example, which is octane, might look totally different than what you would see for, I don't know, cyclohexane, right? Or a derivative thereof. So, really, this is the only type of useful stretch, and that's a CH stretch. I want to go ahead and tell you, though, we're going to have more than one type of CH stretch as we go along our families. We're going to want to further categorize them, and your tutorial actually doesn't really do that, so I want to do it for you. It's important to make note of the hybridization. You know, I misspelled something and it really bothers me, so I have to fix it. You need to know this because the hybridization of that carbon in the CH bond will change the range at which it appears. What you just saw is an example of an sp3 CH stretch. Those are the ones that are between 3,000 to 2,850. All right? And it's not necessarily just alkanes that have them. Any molecule that has any sp3 hybridized CH bonds will have these, right? So just because you see these peaks appear doesn't mean that it's just an alkane. It means that it has alkane portions in it, okay? So keep that in mind as we go along. Whoops, I'm going to go back to this. All right, let's make things a little bit more interesting. Let's introduce a little bit of variety. Let's take a look at, I don't know, an alkene. All right. Now, you know alkenes have at least one carbon-carbon double bond. And so what this is going to do, this is going to introduce a couple of other different types of stretches that we can look for. First of all, there's the carbon-carbon double bond stretch. Whereas the carbon-carbon single bond stretch was buried in the fingerprint region, this one actually does appear in the functional group region. We also have CH stretching. And you can see, you know, if you look here, here, and here, you know, we have our typical sp3 CH stretches, and you do see those. However, we also have H's attached to these carbons as well. So that introduces sp2 hybridized CH stretches. All right, so let's click on alkenes. And boom, you see something a little bit different here. You see this short little peak here at 3083? That is your sp2CH stretch. So that one appears usually from about 3,100 to 3,000 or so. Right? That's outside the range of the sp3CH stretches, so that's definitely going to be something that sticks out at you, whereas, you know, if it's not there, then you probably don't have an sp2 hybridized CH in there. All right? So that's one thing to look for with alkenes. You'll notice that in this example, it's fairly weak. I would say probably the majority of excuse me, allergies are really getting to me. The majority of sp2CH stretches are pretty weak. They're usually very sharp. Occasionally, they'll sort of dip into the moderate range, but not that often. So Usually it's fairly weak. Also, we have the carbon-carbon double bond stretch here, right? And you can see it here appear again as sort of a weak to moderate peak. It can vary a little bit. This one's at 1644, very sharp. All right. Right there. By the way, I'm not going to go through and write all of these down for you, these ranges. You have correlations tables for that. And also, you can write your own notes by looking at the tutorial. It'll probably help you learn a little bit better. I just really wanted to do the first few because I want to differentiate these SP, SP2, SP3 hybridized CH stretches. So I'm sort of taking these along for the ride. But I will sort of taper off doing that as I go along. Also, to make the video more efficient, which was good for everybody. All right, you do see some other stuff here, but again, it's in the fingerprint region. It's not going to be very reliable. Note that you still do see the sp3ch stretching because, hey, you do have sp3ch bonds, but we would still classify this as an alkene. All right, let's try, something else. Let's take a look at alkynes. Now, you remember, alkynes have at least one carbon-carbon triple bond. You know how many different types of molecules we're going to look at that have carbon-carbon triple bonds? We're going to look at alkynes of them. Actually, no, we're only going to look at two. We could have a situation like this. We could have a situation like this, right? The triple bond can be on the inside of the molecule or it could be on the outside. Oh, my wife is telling me something. I'll get back to her in just a minute. She left her phone in the car. Oh, no. Okay, so if we look at this, we have, if we have a triple bond on the outside, that's called a terminal alkyne. If we have one on the inside, that is called an internal. Come on. Now, the reason I'm highlighting this in particular for alkynes is because these will appear differently in their respective spectra. Okay? Let's think about what type of new bonds that we're introducing here. Well, I think one of them is pretty obvious, right? We're definitely introducing that carbon-carbon triple bond. And if we look at the spectrum of an alkyne, all right, you see alkynes appear from about 2260 to 2100. They're pretty sharp, and they're usually fairly weak. One thing that's kind of nice, though, is that's pretty much the only important peak that appears in this region. So if you see something over there, even if it's kind of weak, it's a pretty good chance it's a CC triple bond. Okay? Both internal alkynes and terminal alkynes will have this. Now, terminals are going to have something else that internals don't have. Take a moment, see if you can figure out what it is. Waiting. Okay, spoiler. Terminal alkynes also have a singular H hanging off the end of one of those sp hybridized carbons. Whereas with internals, the sp hybridized carbons don't have triple bonds. Alright? So, that means with terminal alkynes specifically, we can also see the sp hybridized CH stretch. And you can see that over here. This one, it really sticks out. This is the peak at 3324 in one hexine, right? Usually the sp3chs are pretty easy to see. They're usually sort of moderate to strong in intensity, and usually fairly pointy. They're fairly sharp. Really stand out. They're the only things that give a peak with this characteristic shape in this region. They usually appear from about 30 to 3270 or so ish. You'll find that some of these ranges are kind of variable, but somewhere in there. Okay. All right. If you don't have one though, excuse me, if you don't have a terminal alkyne, instead you have an internal alkyne, it gets a lot trickier because that SPCH isn't there. So really the only thing you have to go on with an internal alkyne is that carbon-carbon triple bond stretch. If you overlook it, then it might trick you into thinking it's an alkane. All right, so be sure to look diligently for that. All right, just going down the list here on the left, we've done alkanes, alkenes, and alkynes. I'm going to skip alkyl halides. We're not going to look at that one because, honestly, the only signals that it gives are in the fingerprint region, and they're not very reliable. There are better ways to detect the presence of alkyl halides, so I'm going to skip that one altogether. I'm going to skip aromatics for now. I'm going to come back to it at the end, but I'm going to skip that one for now. Now I want to go into alcohols. All right. So along the way, if you haven't, learned all the functional groups by now, and I'm guessing you probably haven't, you're going to get sort of a crash course and a review in some of them. Alcohols, they have an OH group in them. Okay? So if we're looking at the structure of a typical alcohol, let's say this one, all right, obviously the first thing that we notice is that we have the OH. We're going to have the OH stretch. And this is the dead giveaway that you have an alcohol, because the OH stretch in an alcohol is probably the easiest thing to identify out of all these peaks. And I've shown it to you before. Remember this guy? This big, broad peak over here? That is the indicator of an alcohol OH. Very broad, as you can see. It's if we look at the wave number range, it's about 3,500 to 3,200. Okay, usually moderate to strong, and of course, as you can see, very broadened. Okay, so if you see that, that's a dead giveaway that you have an alcohol group. Of also something to note here as well, there's another type of signal that honestly really isn't that important in identifying alcohols because the OH makes it so easy, but will be important later on. We also have the CO stretch, C single bond O stretch. This is noteworthy because this is one of the only signals that appears in the fingerprint region that we utilize. All right. Again, we don't really have to look at it for alcohols, but it does appear. These peaks usually appear between 1,300, to 1,000, and they appear as a pair of peaks. And usually they stand out a little bit amongst the regular fingerprint region noise. So if you happen to look over here on this one, this alcohol, you see that pair of peaks between 1102 and 1056. Those are your CO stretches. All right, they're usually moderate to strong, so like I said, they stand out a little bit amongst the rest of the noise. Don't really need them here, but we are going to see them pop up in one or two other species where they are more important for identification purposes. Okay. All right. So now we're about to get into a series of compounds that are all kind of related to each other. These are called the carbonyl compounds. All right, and carbonyl compounds all have a carbonyl group, which is C double bond O. C double bond O is the carbonyl group. And depending what else is attached to that carbon, you're going to have different classifications, right? So for instance, R, by the way, in case you don't know, it just stands for a random chain. random carbon chain. If you have at least one H attached to your carbonyl carbon, then it's called an aldehyde. If you have two carbon groups attached, then it's called a ketone. If you have an OH attached, then it's called a carboxylic acid. If you have an OR attached, it's called an ester. Side note, esters are what you love to work with in the lab. Why? Because esters smell good. They smell frequently a lot like fruits. They feel, you might have one that smells like cherries or banana or pineapple or something like that. Some of them also smell like wintergreen and rum, peppermint. So they're kind of fun. All right, and then you also have the amides. And there's three different types of amides. Amides have nitrogens attached to your carbonyl carbon. Unfortunately, I'm going to run out of room, so I'm going to have to erase a couple of these in a second. You could have an NH2 attached. That's called a primary amide. All right. You could have, come on, there we go. You could have an NHR group attached. That's a secondary amide. And you could also have an NR2. Oh, my wife forgot her phone again. My wife is like the worst cell phone owner. She always forgets it. All right, that's a tertiary amide. So what we're going to do is we're going to take a look at, at some of the highlights here amongst these that, are similar but yet very different as well. All right, I'm going to start with the simplest, the one that gives the simplest spectrum, and that's a ketone. All right. First of all, the carbonyl group itself, C double bond O, it really sticks out. It's a very strong peak. Carbonyl typically appears between about 1800 to 1650, depending on the exact group, the exact molecule that you're using. This one we have 2-butanone. We have a peak at 1715, right smack dab in the middle of that range. Very strong, usually very sharp as well, very, very easily identifiable. Now, if you have a ketone, remember, a ketone means that we have two R groups. So, for example, we might have something like, I don't know, this. Now, if you take a look at this, ask yourself, are there really any other, what other types of groups would I have besides carbonyl? Well, other than carbonyl, I really just have CC and CH single bonds, right? All these carbons are sp3 hybridized. So really the only other thing you'd expect to see here would be like the traditional alkane peaks, right? So for a ketone, really what you see is you see a carbonyl and really nothing else that interesting, right? Like I said, the sp3CHs don't really tell you much of anything. So in this example, we see the only one that we can really get any information on is that carbonyl. So by default, we would probably label this one a ketone. Now, with some of the other ones, though, we can start getting more distinguishable peaks that we can identify. All right, and we're going to start off with the aldehydes. All right, so let me just put an example of an aldehyde up here. Yeah, this one will work. Come on. There we go. Okay. So that's an aldehyde. Now, of course, just like any other carbonyl, we're going to have the carbonyl stretch, right? Here you see it at 1731, very identifiable, right? One thing that we see with aldehydes is we see our fourth and final type of CH stretch, right? This is specifically referred to as an aldehyde CH. It's sp2 hybridized, but it doesn't appear where the alkene version of this appears. So this one has its own special category, aldehyde CH. All right, and if you look over here, it says the aldehyde CH stretch appears between 2830 and 2695. And it appears as a pair. There's always going to be two of them. And they can be hard to notice sometimes. They're kind of subtle. They're little spikes. In fact, they're frequently called the aldehyde spikes. All right, and oftentimes they're very easily confused with sp3CHs because they sort of piggyback on the tail end of those clusters. However, the trick is to know the ranges, right? sp3CH stops at 2850, whereas these two here, the aldehyde spikes here, 2827, 2725. So they look like they're part of the same cluster, but they're actually outside the range. So be sure to pay close attention to your ranges whenever you're looking at these little clusters of peaks. All right. All right, so this is a good representation of an aldehyde. All right. You know, my wife keeps bugging me because she's worried about her phone, but I'm going to keep powering on because I care about your education. Please don't tell her that I've been ignoring her text while I've been doing this. I will get to her in just a few minutes. All right. All right, now let's take a look at carboxylic acids. So something like this. All right, so hopefully by now you're sort of getting the hang of recognizing new stuff. All right, so obviously acids are going to have the carbonyl stretch, just like all the other ones. All right, so you can see it over here, 1721. Now, what's the other distinguishing feature of this? You may remember that with alcohols, we saw that the OH stretch was very, very prominent and not easy to identify. So it stands to reason that, yeah, that should be present in acids as well, and it is. All right. Just be aware, the OH stretch looks a little bit different in carboxylic acids than it does with alcohols. Here's what an acid, OH stretch looks like. For one thing, the OH group is even broader than it was before. Whereas in alcohols, it stretched from about 3,500 to 3,200 or so. With acids, it stretches from about 3,300 to 2,500. That's a huge, huge region. So much so, it sort of tends to bleed into other groups, right? In fact, you see it right here. If you follow it from the very left side of the axis, this flat line, then you see it start to broaden at about 3,300 or so, and it's still broadening, and all of a sudden you see that signal, that curve sort of truncate and start going those sharp peaks. That's because at that point that OH stretch is overlapping. It's bleeding into your sp3CH stretching. Then once it gets out of the sp3CH stretch region, it broadens back out and it finally finishes its curve about 2,500 or so. This is a very, very characteristic representation of an acid OH. So do be aware that they look very, very different from each other. Okay, so if you see that this sort of weird amalgamation of peaks plus your carbonyl, you've probably got a carboxylic acid. All right. Let's take a look at an ester. Esters are more subtle. They don't stand out quite as much as acids do. They have something like this, right? So obviously, carbonyl stretch, blah, blah, blah. Come on. Esters, give me an ester. There we go. So yeah, carbonyl peak here at 17. Well, kind of cut off there. Oh, there it is. 1752, right? Very characteristic. If you look at the structure of an ester, this is where you have to really count on that CO stretch. Now remember, we mentioned this with alcohols. The CO stretch, pair peaks between about 1,300 and 1,000 in the fingerprint region, so it's a little bit tricky to dive in. But that is what distinguishes an ester from the other carbonyl compounds. So you need to be able to identify it, or else you might mistake it for a ketone. All right, so over here you can see in this example, we have a pair of peaks, very strong, 1250, 1055. Those are your CO stretches. Combination of those plus your carbonyl indicates that you probably have an ester. Here's another one right over here. Again, you see there's a whole crap ton of noise in the fingerprint region, right? So it becomes very hard to identify, but the CO stretches definitely do stand out a bit relative to the other ones. Okay? All right. All right, I'm going to skip amides for the moment. In fact, it's funny, amides aren't even listed on here. I'm kind of adding them as a special thing. You'll see where I'm going with this in a little bit. Let's take a look at amines. Amines are going to be very similar to amides. They're going to have carbon-nitrogen single bonds. The only difference is they don't have any carbonyls. All right, and just like we've seen before, we can have primary amines, excuse me. Come on. There we go. Primary means if you have an NH2 group. Secondary means if you have an NHR group. And tertiary amines if you have an NR2 group. Come on, let's forget it. I'll write it there. All right. So, what are we seeing new here? Well, for one thing, and this is the main thing, we're going to see an NH stretch. All right. And one thing that's kind of interesting about the NH stretch is that the NH stretch appears differently between primary, secondary, and tertiaries. For this one, for the primary amine, whoops, come on. We see a pair of peaks. All right. So if you look over here, this is a primary amine, right? This is called aniline. You see those two moderate, right? Moderate in size and moderate in shape. Peaks at 3442 and 3360. That's a classic pair of NH stretches, right? NH stretches traditionally appear between about 34 to 3250, similar to the ranges of alcohol OHs, but they definitely look a lot different, so it's pretty easy to distinguish them. And you always see a pair. Okay. Now, if you have a secondary amine, you still have an NH stretch, but only a single peak. All right, so here is a secondary amine, right? And you only have one NH bond there, and you can see that we only have one NH peak. Now, what do you think we're going to see with tertiary amines? We're going to see nothing, right? At least not as far as this, because there is no NH stretch, because there's no NH bonds. And I think we have a tertiary amine on here somewhere. Yeah, you can see here we do not have an NH stretch. All right. NH stretch is going to be the most important thing. You'll notice almost everything else is in the fingerprint region, including the CN stretch. So unfortunately, the CN stretch is not going to be very reliable to look at. The only other really useful one is one that's found in primary amines only, and that's an NH bend. It's our first bend that we see that's important. From about 1650 to 1680. This one actually is a little bit out of range. This one is at 1619. They can go a little bit out of range, sometimes, so I'm guessing that's what's going on here. But usually that shows up as a fairly moderate to strong peak, pretty sharp in this region. Otherwise, really nothing reliable about these. So the main thing to look for is that NH stretch. Unfortunately, because of this, tertiary amines can be pretty hard to identify through IR spec because they really just look like alkanes, right? So for what we have to do with tertiary amines, a lot of times is we have to use some other means of instrumentation and analysis in addition to IR to identify them. All right. Now, like I said, I don't have amides over here to show you. But I think you could probably use your magical powers of deduction to kind of figure out what to look for. For example, if you had something like this. All right, what would you look for? Well, I would think you would need to look for a carbonyl stretch. What else would be important here? Yeah, that NH group, right? And it's a primary amide, so you can probably figure out that we would see a pair of NH stretch peaks as well. So basically, these follow the same rules as amines, except that we also see a carbonyl group with them. Okay? All right. All right. Now, one last thing I want to show you, and that's going back to aromatics. All right. Now, again, we've touched on aromatics here and there. We're going to, get into them more in organic too. But I mentioned earlier that aromatics. Oh shoot, my whiteboard reloaded. Okay, give it a second. It's has to load for a second to get its little toolbar up. La 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 la. There we go. Okay, so aromatic groups basically are cyclic structures that have a very specific, delocalized set of electrons inside them. Probably the most common one that you'll run into is benzene, or some sort of derivative of benzene, meaning something else is attached to the ring. All right? But we can use benzene as a good example here. If you look at benzene, it's got 6 H's, 1 each, that are attached to the respective carbons of the ring. Sorry. All right. What's the hybridization of each one of these carbons? sp2, right? So guess what? You remember when we talked about sp2ch stretching with alkenes? We also see it with aromatics as well. So, if you take a look over here, right, we said they appear between about 3100 and 3000. You can see a couple of them pop up here at 3099 and 3068. All right. So that's one thing that makes life a little bit difficult sometimes with aromatics, is the fact that their CH stretching does mirror that of an alkene. However, there's a couple of other things that you can look for to help distinguish these from alkenes. You'll notice also you're going to have carbon-carbon double bonds, right? So you're going to see carbon-carbon double bond stretches. However, this is a little bit different, because one thing that you're going to see about aromatics once we get in the second semester is that they have a lot of resonance. So actually, these electrons are constantly moving around, and the fact that they're constantly delocalized makes the C double bond Cs a little bit different here than they are with alkenes. All right? So you still see the stretch, right? But the range is shifted, all right? Look over here. And they, in fact, they don't have full double bond characters, so they actually list them as single bonds, but you can think of them as double bonds as well. Where it says CC stretch in ring from 1600 to 1585, there's a peak. And then you have another one, CC stretch in ring from 1500 to 1400, just into the fingerprint region. These usually appear as a pair of peaks, one of each in those ranges, or close enough. This one has one at 1614, and then one slightly outside that range at 1506. But again, we can say there's a little bit of variability in ranges sometimes. Usually kind of moderate, sometimes kind of strong, usually very, very sharp and pointy. Alkene C's double bond C's appear between 1680 and 1640. So you see the ranges are a little bit different. So there's sort of a subtle point, but one that you can use to distinguish aromatics versus alkenes. All right. The last thing to look for is something that I'm actually going to go into more detail on in second semester, or whoever's teaching the class. And that is something called OOP bands, or out of, let's see, come on. Dude, come on. Thank you. Out of plane bends. They're called OOP bands for short. Kind of catchy. Basically what that means is if you have, an aromatic ring and it's got bonds, I keep wanting to draw it one way, but then I remember you guys haven't had organic too, so I have to do it this way. Alright, so let's just put some stuff here. Let's put some H's. Oh, let's put a methyl group there. We'll put a Br here, blah, 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 whatever. Alright, so a benzene ring, or an aromatic ring, is basically as flat as a sheet of paper. Right? It's all contained within one plane. The bonds that are attached to it, whether it's an H or a Br or CH3 or whatever, they can sort of wag up and down, constantly sort of wagging slightly above and slightly below the plane. Right? That's called an out-of-plane ring bend. All right? And those create something called OOP bands. All right? OOP bands are probably the most important signal in the fingerprint region. They appear way over between about 900 to 675, and they're usually pretty strong. Right? You can see here, we see an OOP band at 738. Very, very strong. They're usually kind of sharp to moderate as far as their shape goes. And one interesting thing is that you can see different types of OOP bands depending on a bonding pattern. Right? That's something that we haven't really gotten into, so I'm going to leave it off for now. I might make a separate video to describe that in more detail, to give you a preview of Organic 2. Let me think about it. But for right now, if you see strong peaks appear in that 900 to 675, that means you probably have an aromatic ring. All right, that is enough of me prattling on. I think you guys would have enough to digest between these first two videos. Please watch these. Try to get the material down. I don't expect you to memorize everything, but sort of get a general lay of the land, and then next week we will do practice problems together. Until next time, have a good one.